So when your needle's like over here at 3, that's really like 3,000 RPM, revolutions per minute. Think about that. That's, how many revolutions is that per second? That's 25 revolutions per second. So spinning is 20, it goes around a full revolution 25 times in 1 second. Actually, 1,500 RPM is not very fast. Not very fast. I have I do some woodworking and stuff, and I have a router, right? That router spins at 16,000 RPM, 16,000 revolutions per minute.
You're a carpenter.
I wouldn't say carpenter.
So at that RPM, your spark plug is sparking 6 times every second?
Yeah, 25 times. It's going to go it's spinning 25 times per second, and it takes, it's a 4-stroke, so it's going to fire on once every 4 times it goes around.
Yeah. These things last for years.
Yeah. Yeah, those spark plugs fire millions of times before they fail. Yeah, when you start to really analyze how good we've gotten in terms of our machinery, it's pretty impressive. All right, that was a bit of a problem there, huh? But that kind of brought a lot of things together, right? Geometry that we're not familiar with, like law of cosines, we don't bring that out very often, right? But it goes to illustrate again, like every single one of these problems is different. The geometry, you're just gonna have to look at what you have, figure out what works. All right, let's see, it's 2:13. This is a good break time. If we're gonna do a break, this is a good time to do a break. I have to show you this problem. This is just a classic problem, like really, really classic problem. But it's really straightforward. There's not a lot of, like compared to what we just did, this is like very basic. So let's take a break. We're gonna take a 10-minute break. But if you want to, you can start looking at this because I'm gonna move through this problem extremely fast. So we'll come back at 2:25. And then we're going to grind the rest of the way, right? So we're going to go from 2:25, we're going to go all the way to 4:30. So, but we're moving out of this section after we do the ladder problem. All right, have a good break. So take a look at this problem here. You've got a ladder leaning up against the wall, and the ladder slides down the wall at a constant rate of 0.5 feet per second. And the question is, at the moment the top of the ladder is 3 feet from the ground, how fast the bottom of the ladder is moving away from the wall. So it's kind of like you got this ladder up against the wall and it does that. And so, So we are going to draw a picture first, right? So here's my wall. You can put your wall on the left or the right. Here's my ladder. And the ladder's 20 feet tall, right? 20 foot. So that's never going to change, right? The ladder's length is always fixed. And what's happening here is that the top of the ladder, which is this point right here, is moving down. And at the same time, this point here is moving to the right. And since those two sides are changing, I'm going to call the distance from here to here, I'm going to call that y. And then I'm going to call the distance from here to here, I'm going to call it x. And this is my general picture. Now, at the instant in time that we're talking about, I have that same picture, but my ladder is now, see, at the moment the top of the ladder is 3 feet from the ground, so I've got something like this. This is 20. This is 3. Of course, that's a right triangle there. And if I know those two sides, then I definitely am going to be able to find that other side if I need it, right? Okay, so just going to put a little check there. I know I can get that if I need it. The height, it says the distance, right? At the moment the top of the ladder, right, is 3 feet from the ground, right there. What am I given? Sorry, what am I given? What do I want? So I'm given, go ahead.
X is growing by 0.5 feet per second.
Is it x? You sure? The ladder slides down the wall such that the top of the ladder is moving downward. So this top is moving downward at 0.5. So it's actually the other way around. It's dy, right? dy dt is negative 0.5 feet per second. I'll put what I want underneath it. What I want is how fast x is changing. I want to know how fast the bottom of the ladder is moving away from the wall. So I want to know the speed at which that point at the bottom is moving away from the wall. And I want that at the moment that y is 3, right? So I want to know how fast is this point moving this direction at exactly the moment that this is 3. The y value here is 3. And so now we just need an equation. Pythagorean, right? Go look at your general picture. We have x squared plus y squared is 20 squared, right? That's our equation. And it has x and y in it, right? No other extraneous variables that we don't need. So I can differentiate that with respect to t. So implicit 2x dx dt plus 2y dy dt equals 0. So I have to do some chain rule, right? Derivative of x squared is 2x, but then derivative of x with respect to t is dx dt. Plus derivative of y squared is 2y, but then derivative of y with respect to t is dy dt. And then derivative of any constant is 0. Now I just check to make sure I have everything I need. Do I know x at the moment in time? No, not directly. I'm going to have to go get it. dx dt. That's what I'm looking for. Okay, y. Do I know y at the moment in time? Yes. Do I know dy dt at the moment in time? Yes. Okay, so I just need to go figure out what x is real quick. And to get x, I can come back to this triangle right here. Right, this was x. And just Pythagorean. Just Pythagorean. So I know x squared plus 3 squared is 9 squared. I mean, sorry, is 20 squared. So 400 on the right side, 9. 400 minus 9, 391. X squared is 391. And then you can take the square root on both sides. 19.7? Is that what you said? Okay, so x is about 19.7-ish. I'm not real big on, how many decimals we're going to round to. I mean, we can always get real anal about that, but I'm not going to. All right, now we plug in. You could kill off a 2 from each of these, just divide both sides by 2. I'm not even going to worry about that. I'm just going to plug in. So 2 times x, 19.7, times dx dt, which is what I'm trying to solve for, plus 2 times y was 3, times dy dt, which was negative 0.5. That must equal 0. And then you solve for dx dt. So I would just multiply these together, take it to the other side, divide by this, and you're done. I'll let you finish that. Are there any questions? That one I think was a little more straightforward, yeah? Another thing I've been known to do on tests is when I get to the related rate problems, I give you like problem A, problem B, problem C, problem D. And let's say that this is let's just say that this is number 5 on the test, okay? I give you 4 problems to look at. And if number 5 is worth 20 points, what I'll do is I'll say problem A is only worth 15 points. Problem B is worth 20 points. Problem C is worth 22 points. And problem D is worth 25 points. In other words, I may give you something where A is an easy problem, like the ladder problem. And yet, you can do it. It's straightforward, but you're only going to get 15 out of the 20 points possible. If you do problem B, that's like a little bit harder, then you could get full credit. And then I give you 2 more that are like more challenging, and that almost acts like a bonus. That make sense to you? I've been known to do that as well. I'm just telling you. It's, I'm not sure what I'm doing yet. Yes?
So would we only pick one?
Yeah, this you'd be pick one.
Okay.
Or I might make it where this is worth 40 points, and you pick 2. And then you could theoretically, pick this one and have a bonus. Yes?
So like with that, could we try more than one on the test? And then
Well, you would have to tell me which one you want me to grade.
Can we do all
So-
4 of them?
Yes, but you would have to tell me which one you want me to grade.
Can we say whichever one's right?
No. You have to tell me,
Right.
these are the ones I want you to grade. All right. Did anyone happen to get that answer? 0.076. Anyone else get that? Yeah? Okay. 0.076 feet per second. All right, we are going to wrap this up. All right, we are wrapping up chapter 2 in terms of our schedule. Right, we are done here. And we're going to move into 3335, all right? So chapter 3, section 1 and 2, which is not on the calendar here, sections 1 and 2 are a review from college algebra of exponential and log functions. So I'm going to do a very quick review, just so we all know what we're talking about when we say exponential and log functions. This is not something I'm going to write down all the notes and go through examples. This is more of like, hey, do you remember this? If you don't, maybe you should go back and review. All right. We're in chapter 3, which is called inverse functions, and 3.1 is called exponential functions. So this is me just saying quickly, I'm going to go through this. So try and remember, if you can, that in college algebra, we had these things called exponential functions that look like this. F of x equals a to the x, where a is greater than 0 and a is not 1. So examples of this were things like f of x equals 2 to the x, or maybe we had f of x equals 1/3 to the x. The idea here is that your x is in the exponent, your variable's in the exponent, not in the base. And the base is a number. And that number has to be positive and it can't be 1. And those are called exponential functions. And when you graph them, they look like this. Well, kind of. This right here is a graph of the exponential function f of x equals a to the x if the a that we have is bigger than 1. So if the number down here is bigger than 1, like this example 2 to the x, then our graph should look something like this. And we call this exponential growth. So what we want to do here is remember, like from when we were talking about limits, that if I give you the graph of a function, if I ask you what's the limit as x goes to infinity of this function, that means as you go to the right, what does this exponential function do? It takes off to infinity, right? So that's what this first thing means, right? And then if I go to negative infinity, that means I start going out this way. The graph dives down towards the x-axis, approaches the x-axis, asymptotically approaches that, and gets closer and closer to 0 without actually ever getting there, right? That's what it'll look like if the a is bigger than 1. Now, if your a is smaller than 1, but still positive, like a fraction, like 1/3, then what does it look like? You'll know? It's not exponential growth. It's exponential decay. It goes the other way around, right? So if the number in here is positive but smaller than 1, then your graph does the reverse. If you go out this way, it asymptotically approaches 0. And if you go this way, the blue one goes up to infinity, right? So again, that's just a quick review of what exponential functions look like and how they're defined. Why do you think it is in college algebra that we say that a can't be 1? Yeah, what's 1 to any power? It's 1, right? So then the graph would just be 1. It'd be flat, wouldn't it? Which is not what an exponential function should look like. And then, why don't we do negatives? Like, why do we make sure that this is never a negative number? Well, because if you raise negative numbers to certain powers, you get imaginary numbers, and things get weird, right? Like, imagine I defined something f of x equals, let's go -1 to the x. And then I ask you right now to plug in a half. Then this would be -1 to the half power. Bless you, which is the same as square root of -1, but what's square root of -1? Well, that's a problem, right? So we just totally throw out all the possibilities of having a negative in the base, and we categorize any function that has a base where it's positive, but not 1, as exponential functions. Mathematicians do look at this, but just in terms of what an exponential function is, we don't think about this. All right, next thing. Properties of exponents, all right? Properties of exponents. One thing we need to know is that if you have an exponential function, right? If you have an exponential function, a to the x, that it's continuous everywhere. So when you draw, you don't ever have to pick up your pencil, right? You could tell from those two drawings, right? We'd never pick up our pencil. So they are continuous functions. We also have these properties of exponents that we've been using throughout this class and classes before, that if you ever have something to, well, if you have something to a power times something to a power, if they have the same base, you add the exponents. If you have division, same base, you subtract the exponents. And then if you have something to a power, you multiply the exponents, right? Those all look familiar to you? Properties of exponents?
And do we have those on our formula sheet?
Those, I think, are on the formula sheet on maybe the very first page on algebra. And then this one, that if you have two things being multiplied together and you take all of that to the x power, that you can apply the x to each one. So this, again, just college algebra properties. That's it. That's all I'm going to remind you. But I do want to give you one thing. If I said, look at this function, f of x equals 4 to the negative x. And I ask you, what's the limit of this as x goes to infinity? Right? There's a few ways you can look at this. It's 0. Let's see why. There's two or three different ways you can do this. One way is this. I can rewrite this as 1 over 4 to the x. Right? Remember that if we have something to a negative power, we can drop it down and make it 1 over that to the positive power. And now, if you just think about it, right? If x gets big, what's 4 to raised to a big number? Big number, right? So the bottom is headed to infinity, and the top is fixed. And anytime you have fixed over infinity, that goes to 0. Right? Remember, limits. That's one way you could do it. Another way you could do it is, instead of this, look at that right there and agree with me that that's the same as this. Do you all agree that's the same thing? Because if I did this, I would apply the x here and here. So what's 1 to any power? No, what's 1 raised to any power? 1. So the top is 1, right? And the bottom is 4 to the x, right? Which is this. And if I write it this way, then the base here, right, that's my a, is less than 1. And we just said that if a is less than 1, it looks like this, right? And if I want to know what's happening as x goes to infinity, you can see from the picture that it's going to 0. So there's like a bunch of different ways you can understand this. The most important thing is that you have a way to do it, right? I don't care which way you look at it. All right, let's get to logarithms. Logarithms, the reason we introduce the idea of a logarithm in college algebra is because we try and find a function that undoes an exponential function. So we have these exponential functions and we say, hey, I wonder if there's a function that would basically undo what that function just did. And that's where the logarithm comes into play. So logarithm functions. So here's how we define logarithmic functions. We write them like this. This is 3.2. F of x equals, the way we write logarithms is log base a of x, like that. That's the way you write a logarithm. And we have the same restrictions on a. A has to be positive and a can't be 1. And the reason why it has the same restrictions is because this is the inverse of an exponential function. So whatever restrictions we had for the exponential function will carry over to its inverse. And so that base, the base of the log can be any number. Base can be any number. So we have log base a. If the a is positive, this is what a logarithmic function looks like. And there's something very important about logarithms that is not the same with exponentials. This is your y-axis, right? The graph of this function only exists to the right of the y-axis, which means, if you recall from college algebra, you cannot plug negative numbers or 0 into a logarithm. If you try, then your calculator will say undefined, right? So you cannot, there should be no graph to the left of the y-axis. It should be purely to the right. And so if I try and say what's going on if x goes to infinity, this graph grows, right? As I go out this way, it grows. It doesn't grow very fast, but it does grow. And just keeps going up and up and up slowly. So as I go to infinity, this function goes to infinity. Now, I can't ask you to go to negative infinity because there is no picture over here. But what I can ask you to do is to approach 0 from the right. And if you see what happens here, it dives down to negative infinity, which is where this comes from. Does that make sense? Do these look familiar, these graphs? A little bit? This is if a is positive. Let me show you what happens if a is negative. Anyone know what it looks like? Like that.